Hello physics students, welcome to video 6 where we're going to look at forces and Newton's laws. And again, this is a recap of what we know plus reinforcing things that we just need to know a little bit better. So in terms of forces, we can have balanced and unbalanced forces, and we'll go through a couple of examples of those scenarios. So when you're just sitting on a chair, you have your weight force. And your weight force is your mass times the acceleration due to gravity. And that's pushing down on the chair. And because this is a scenario of a balanced force, because you're not moving, the chair must push up with an equal and opposite force. So generally speaking, if an object's not moving but it's experiencing a force, there must be another balanced force that's sort of counteracting that force. Not sort of, it is. And therefore the net force is zero. And so in this scenario we would say the net force that the person's experiencing is zero. That doesn't mean that there's no forces acting on the person. Again, here's a truck. Here's someone pushing one way, someone pushing the other way. If they're both pushing with an equal but opposite force, the truck stays still. Again, here's a table. You might think there's no forces acting on the table, but there is. There's a weight force due to gravity, and the table must push back with a reaction force, and so that's a balanced force. Okay, there we are. And again, a person is balanced as well. Why I kept these slightly pixelated pictures in, I'm not certain. Now, for unbalanced forces, if you remove the other person pushing in the opposite direction and you only apply a force in one direction, the truck will move to the right. And if there's no other forces acting on the truck other than this pushing force, it will accelerate because F equals ma. In the more real world situation, here you have the force provided by the engine, which is 100 newtons. Here you would have your air resistance because of the chunkiness of the truck. And so overall, you would say that the net force, if we did a quick little vector addition, we would get a net force of 40 newtons to the right, and therefore this truck would speed up. It wouldn't travel with a constant velocity, it would speed up. And so unbalanced forces cause an acceleration. Alright, so back to our book. That's probably why I kept that other one in, is that this is a variation. So we have our book, but now we're applying a force parallel to the table. And so whilst that force is being applied, we would get a acceleration or a movement of that textbook. And if the force was greater than the friction force, the book would accelerate. If the force was not greater than the friction force and was being got over the initial threshold to cause the book to move, the book would then move with a constant velocity. So Newton's first law, if we go, so that was all balanced and unbalanced forces. So if we go into Newton's laws, which pretty much talks about forces, Newton's first law is all about balanced forces. And so when they're balanced, you have no acceleration, but that doesn't mean that the body is not moving. And there's a common misconception that if a body is moving, it must have a force on it in the direction of its motion. But that's not the case. It's only got a force in the direction of its movement if it's accelerating. Otherwise, all the forces are balanced and it's moving at a constant velocity. Okay, now, so we can, but Newton's first law applies in two scenarios where the objects are at rest, they stay at rest, or an object in motion, but because the acceleration is zero, it stays in motion. So it just keeps going. Students do get a little bit confused about that second scenario. Now, Newton's second law is about unbalanced forces where you have an acceleration, and that acceleration could be a positive or a negative. So it could cause an increasing in velocity or a decrease in velocity. It could cause a change in direction as well. And so in this case we've got this cart being pulled in two directions by different forces. The net force if we did our vector addition, would be 2 newtons to the east, and that would be the force that causes the acceleration. Another common misconception is that in this sort of situation, students might recognize that the cart is moving. They may or may not recognize that it's then accelerating, but it is accelerating, and if it is accelerating, they want this whole 5 newtons to cause the acceleration. But it's not, because 3 of the 5 newtons here are balancing these 3 newtons. And so only 2 newtons of force are being applied to cause the acceleration. And Newton's third law is about for every action there is an equal and opposite reaction. When an object applies a force, an action, to a second object, the second object applies an equal and opposite, a reaction, to the first object. And in physical science we went through all these examples, so hopefully you've got your head around those scenarios. Now, the next thing we need to be certain about is the difference between weight and mass. Again, we did this in physical science, but you may have forgotten it. Weight is measured in newtons, which tells us it's a force. Mass is in kilograms, which tells us it's a measure of the amount of matter that something is made up of. And so, because F equals ma, and often we're talking about the weight on Earth, sometimes we substitute in the equation W equals mg, where the force is represented as a weight and the mass times g, which is gravity. I prefer not to do that because in physics we don't just limit ourselves to Earth. We look at the whole universe. And so if you're interested in the weight of an object, it's much better to recognize that it's just a force, and we can use a subscript Wt or weight to represent that we're looking at weight force. And no matter where it is in the universe, the weight force is going to be the mass times the acceleration it is experiencing. And so let's not limit ourselves just to Earth. But let's compare how that works. So here you are sitting on or standing on the side of Earth. Let's say you're 50 kilograms on Earth. You have an acceleration due to gravity of 9.81 meters per second to the minus 2. So your weight force is 490 newtons. Now on the moon, because the moon has a smaller mass, and when we start to do gravity, you'll realize that the acceleration due to gravity is the measure of the gravitational field strength, and therefore because the moon is a smaller mass, you have a smaller gravitational field strength, and therefore you have a smaller acceleration due to gravity on the moon. And that acceleration due to gravity on the moon is only 1.6 when compared to 9.81. So that's why the astronauts felt considerably less heavy on the moon. Now, apparent weight also applies to situations such as elevators and when in free fall. And elevators are a topic that examiners seem to love. And so you just need to make sure you get your head around it. In Launceston, we have one elevator that goes up, gives you a small amount of experience of up and down forces. If you go to a skyscraper in a bigger city, you'll experience this much more firsthand. But the scenarios are going up and where you're speeding up. Now, if you're going up and speeding up, that means you're accelerating. And so what you would have is you would have your weight force. Now, your weight force is constant, and so that won't change. But you'll have the acceleration due to the speeding up, and so you'll feel that, and so the normal force or the applied force is much greater than just the reaction force to your weight force. So you feel heavier, and you feel a push down. If you're going up and slowing down, you would actually feel lighter. Now, why do you feel lighter? Because your weight force is the same, but you're slowing down, and so there is actually they've drawn this arrow around the wrong way. Let's fix that up. Where's my pen? There must be a force going down that's causing the deceleration, and then when you add the weight force to the deceleration force, you get the normal force, which is less than your weight force. Okay, and that's why you feel lighter. And you could do the same situation with going down, where you would speed up as you go down, and then when you slow down as you come to the level you've got to stop at, you feel heavier. And what you can do in a lift is at various points you can jump up and down. Do this in a crowded lift, and you might get some funny looks. If you're especially in a skyscraper, one that goes to the higher floors, they go very fast, and there's laws that regulate how fast they can slow down or speed up, because if you didn't have physics and you just let the engineers design the fastest lifts they possibly could, when you got into a lift to go to the 99th floor, all of a sudden it would accelerate so quickly that everyone would fall on the floor and wouldn't be able to lift themselves up. And then once it stopped accelerating and reached its maximum velocity, you'd be able to stand up all right. And then once the lift started to slow down very suddenly as it reached the floor, everyone would suddenly feel almost weightless and may lose a little bit of control over where they're standing, and then fall over or even bump their head on the ceiling, which you don't want. And there have been cases in certain countries where in these sky rises they didn't test them enough, and fit adults were okay, but then someone who was overweight or someone who was elderly or predominantly overweight or elderly got into the lift, and they would get to the floor with a broken leg or a dislocated hip or something, and it was all because the forces were too great. But back to what I was saying is, if you get the chance to go in a super fast lift, do and make sure you jump up and down at various stages in your going up and going down. And if you're going in a fast enough one and you time yourself right, you should be able to just hit your head on the ceiling and have a little sensation of weightlessness, which is fun. Alright, now free fall is, we looked at this in physical science, so this is when you're dropping something, and we do consider air resistance, and we reach what would be called the terminal velocity. And the terminal velocity is where the drag force due to air resistance is equal but opposite to the weight force, and therefore the net force here is in equilibrium or zero, and so no more acceleration occurs. So if we looked at a skydiver or a ball that's being dropped from a tower, initially it accelerates at 9.8 meters per second because there's no air resistance, but air resistance is proportional to velocity, so as it gets faster and faster you get more air resistance, and then eventually you reach terminal velocity. And the rate at which you reach terminal velocity is dependent on your drag coefficient. Okay, and you look at skydivers, they alter their drag coefficient by altering their shape, and that's why these guys are able to, they're doing it head first, so they've got a fairly low drag coefficient, whereas other people spread themselves out in all sorts of different ways, and they can move around and do all sorts of tricks. And I think on our OneNote there's a whole lot of videos of people doing interesting things whilst jumping out of planes, and it's a pretty interesting sport. In the future they're thinking of jumping out of spacecraft, and what they're doing is these tourist flights that are going to take people eventually up to the edge of space and give them weightlessness. Some of them will be designed to open up and allow people to jump out, but to do that you'd have to have a special suit that would be heated and cooled, because some of you at one stage you'll get very cold, and at another stage you'll get very hot as you get friction from the surface. Up in outer space it's very cold, and so you'd have to have a complicated system that did that. You'd also have to have an aerodynamic system and probably an automatic chute opener, because if you went into a tumble or a spin and went unconscious for one reason or another, you'd hope that the parachute would still open for you. And this is the plan that people are trying to do in the future. People are already designing these suits, and the highest anyone's jumped is about 40 something kilometers. Now there was a guy who did it with Red Bull, and there's some videos on OneNote about him. And then another guy who was a Google executive decided to jump out and to break that world record, and he did it very quietly without lots of Red Bull labeling, but he now holds the record. And there's also a video of someone who did an animation of what it would be like to do this sort of stuff, and it would be cool, it would be fun. Right, in the next video we'll look at inclined planes, which is not nearly as much fun as jumping out of a spacecraft, but is interesting all the same. Cheerio!